is we're going to start talking about similar triangles. So similar triangles talk about many different things, but right now we're just focusing on triangles, no other geometric shapes. So that's important for you guys to know right now, okay? So the first definition here is to explain the definition of similar. It doesn't mean identical, so you have to know that difference. It's very important. What it means is that it's corresponding in side or amount to something else. So that means that it's not identical, but it was multiplied by the same number to get the side lengths proportional to the other, or it means that the angles will be identical to each other. That's what represents it as similar, okay? And so then our next definition is similar triangles. Now, similar triangles have two criteria that they need to be satisfied, or two conditions that need to be satisfied. However, because it's triangles in particular, you only need to satisfy one of them. So you only need to prove one of the two conditions in order for you to be able to automatically prove the second one. But that only works with triangles. Okay, remember that for our next lesson, please. So corresponding angles are equal in measure and corresponding sides are proportional in length. So we talked about angles. We know what an angle is. We know what equals means. We know what sides means. We know what proportional means. What in the world does corresponding mean? Well, that actually is my next definition here. Corresponding, it means that you have the same relative position in geometric figures. So for example, if I was to put that into an everyday term, when you guys sit in the same spots you sat in the day before in class, that is in a corresponding spot. So what we want to discuss is the major components of similar triangles. So just going off of here right now, label the sides of your triangle, but when you label a side, you use lowercase letters only. And you can't just use random letters if your angles are already determined. So for example, this guy right here, this opposite side here, so I'll put the word opposite. This opposite side right there, it is opposite from angle A. And notice how the angles are identified by uppercase letters. So that means that with that being the opposite side right here, this 9, this side right here that has a value of 9, it's actually equal to lowercase a automatically. And that's the same idea with B. So the opposite side of B is going to be 15. So therefore, this is lowercase b. And then, of course, you have C. So this right here is the opposite side. It's the side that's not touching the angle, basically, how you look at it. So this right here is C equals. And then going off into your next triangle, this is equal to lowercase e. This is equal to lowercase f. And this is lowercase. Name off your angles and your sides of your triangle. So what you want to do is you want to talk about the corresponding sides at this point here. And so corresponding sides are which ones are the same, which ones are in the same position on both triangles. So for example, if this B, this side B here is a diagonal side, what you want to do is you want to go find the diagonal side on this triangle right here, and that is going to be considered its corresponding side. Therefore, we'll mark down little notes of B corresponds to F. Okay, so a little note that we have here for ourselves. And then we have that A, this is a horizontal one, so therefore we go and look for the horizontal one over here, which is E. So A corresponds to E. And lastly, we have our vertical sides here. So C corresponds to G. So quick little reminder, corresponds means that they're in the same place on both triangles. Now, what is the scale factor that was used in order to go from this triangle originally, this actual triangle, all the way to this triangle right here? And so by looking at that, we're going to discuss how to figure out the scale factor. So just a quick little reminder that the scale is always the diagram divided by the measurement. So number 2 divided by number 1. And if it doesn't tell us in the question which one is number 2, we just automatically assume the one on the right hand side is the second object that was made, okay? So for example, if we do the B corresponds to F, we would then go, okay, 5, and then we're going to divide it because this is the diagram divided by the actual. And so in this case here, it would be 5 divided by 15, but that gives me a simplification of 1 over 3, so 1/3. So that means that I times this number by 1/3 in order to get a value of 5. And I want to prove that I did the same multiplication to 12 to get to 4 and the same multiplication from 9 to get to 3. That's what we have to prove right now. So the scale K4, I'll just move this up here. So the scale now to go from A to E was 3 divided by 9, which equals 1/3. Perfect. And then to go from B to F, okay, so the scale was equal to 5 divided by, oh, I'm sorry. We've already done that one. So we have to do actually, let's see here. What do we have to do? We have to do C to G. That's what we have to do. So 4 divided by 12, which again simplifies to 1/3. So that's perfect. Now, quick little reminder for you guys, this right here proves that our scale factors are in fact equal, which means that all of these sides were properly multiplied by the same number in order to get these sides here, which means that these sides are proportional to these sides, which automatically means our triangles are similar. However, what I want to show you guys is how to prove it if you only know the angles, because you could have one of two conditions. So the second portion to all this is if you look now at what we have here. Sorry, just trying to fix this up. Okay, if you look here what we have, so we want to look at the corresponding angles. So the one at the very, very top here is corresponding to this. And as you can see, it was side A corresponded to side E, which automatically means that angle A corresponds to angle E as well. Okay, and so because these two angles are equal to each other, that automatically states that in fact they are starting off on the right foot. And so then we would write it down here. Sorry, we'd write it down here that angle A, and so that L that looks really like slanted and weird, that represents angle. So I'll just add that up here very quickly. Angle, or this L slanted, it equals the word angle. Okay, so angle A is equal to angle E, which is equal to 37 degrees. So that is perfect. That's exactly what we want. So it corresponds to angle E, which is equal to 37 degrees. Now, box right here that you guys see on either one of these, that box represents 90 degrees. So angle B is equal to angle F because they are both equal to 90 degrees, which is exactly what you want because they are, in fact, corresponding angles. And finally, you have angle C and angle G, but those are the only ones that we don't know their value. In order to find that value, we have to do a little bit of math, because what we do know about all three sides is that the sum, so adding them together, the sum of these three sides has to be 180 degrees total. So what you get here is a little bit of math just off to the side here. Actually, where am I going to put? I'll put it more up here. I'll back it up a little bit. So in order to figure out angle C, I had to do 180 degrees, and then I'm going to subtract the two angles that I know, and that will give me a value of degrees. So your 53 degrees is for angle C, and because it's the exact same numbers in triangle EFG, angle G would be identical as well. So then we go back to our work here to show off our work. And so we have angle C equals angle G, which equals 53 degrees. Okay. Now, because we have now proven at least one of the two conditions are in fact satisfied, that then means that we have automatically similar triangles. So how we would answer that final portion is we're going to use a triangle ABC, and now we're going to use one squiggly line. And that one squiggly line is very important for you to know. It signifies the words is similar to. Okay, and it's similar to triangle EFG. And that's what we wanted to prove. So now just going to look at the notes very quickly down here. Angles are represented by an uppercase letter. Oops, sorry, letter's already there. So an uppercase letter, and the sides are represented by a lowercase letter. And the symbol, one squiggly line, not two. Two squiggly lines means approximately equal to. One squiggly line signifies is similar to. Very important for you to know this kind of stuff. Might be good for you guys to write on your cheat sheet if you're interested. Okay. All right. Now, very last question to go through. Pretty important one as well. All right. So let's see here. Let's get this focused. There we go. All right. There we go. Okay. So we want to use, okay. We want to use similar triangles to determine the missing side of one of the lengths here, okay? So what we're looking for is trying to find the value of x right here, and that is the long side here. And I don't know if some of you can see it yet, but we're working with a double triangle. So we have this big triangle right here, and then we also have this smaller triangle right inside of it. And so if you can't see that very well, my recommendation to you would be to split these triangles up. So how do we split them up? We have the big triangle right here. Okay, 90 degrees. And what it says is this is x and this is 9 centimeters. And how did I get that is because this small amount plus this amount right here gives me the total right there. So I did 3 plus 6 equals 9 centimeters. Okay, so that's just a little note for you guys there. And then I have my smaller triangle just inside of it, and actually it's also got a 90-degree angle, and this is 6 and this is 5 centimeters. Now the problem here is that we want to use proportions in order to figure this out, but we don't actually know, two corresponding sides. We know both their values, which is great, but then the problem is we need to know another set of corresponding sides. So we don't know this, so we need to know its number right there. We need to know its corresponding side's value. So how do we figure that out? Well, if you have two sides of a triangle and you need to figure out a third one, you have to use your Pitt theorem. That is correct, guys. We're going back to grade 8 here a little bit. So we have 5 squared, and sorry, that starts with the a squared plus b squared equals c squared. So we have 5 squared plus 6 squared equals c squared. So that means that we have 25 plus 36 equals your c squared. And then if you add that all together, you get a total of 61. Now the problem is I don't care about c squared. What I care about is c. So what is the opposite? What operation will get rid of something squared? It's when you square root. And that cancels that out. And therefore, your answer is a value of 7.8 centimeters equals c. And so that right here, we can mark it down if you'd like. You can also put it inside this triangle if that's what you prefer to work with. Okay, so going off of all of that now, what we know here, there we go. So what we know is the following, and what we do know now is that we have proportional sides. So we know this is 6, we know this is 9. I need to pick one of them as being my diagram, one of them being as my actual, because we don't really know which one came first. So let's pretend I picked the big one as my second. Why? Just because you could have gone the opposite way, that would have been fine. But you go 9 divided by 6 equals. Now the important thing is you just remind yourself where the x goes, where the 7.8 goes. If 9 is a part of this triangle, so is my x. Therefore, my x must be on the numerator. And that is the same idea with the 7.8. Part of a smaller triangle, so therefore it has to be on the denominator, as was my 6. Okay. So then here we do a cross multiplication, and then we divide it. So you have 7.8 times 9 divided by 6 equals x. Therefore, your value is 11.7, centimeters is equal to x. Oops, can't see that right now. Hang on here. There we go. And that's what you have. Okay, guys, so I know this was a little bit of a longer lesson, but it's not typically always going to be like this. This was a little bit, would have taken a little bit more time in class for sure. Feel free to review this video if you have to, and please, guys, please email me questions, but if you would like me to start a private chat, so you can chat with me on the Teams app, which is typically a little bit quicker, then I'm happy to do that for you as well. Happy math!